Welcome back to our video module on quantum mechanics. In a previous video, we took a look at the free particle moving across an infinite delta function well. Mathematically, we modeled it as a free particle wave moving in with some amplitude A, some of it being transmitted with C, amplitude C, and some of it being reflected, amplitude B. And we basically use the time-independent Schrödinger equation to model the behavior. Today, I'd like to change the potential profile so that now we have a finite square well of some given width, in this case 2a, and depth v0. How will this affect the behavior of the free particle? Will it still transmit and reflect, or will some other things go on? Today, we'll be looking at a free particle movement across a finite square well, starting with our time-independent Schrödinger's equation, and setting up the forms of the wave equations so that we're ready to identify solutions. So let's take our delta function material and move it up into the corner. That way we can at least look back and reference, because this potential profile is going to exhibit some of the similar behaviors as what we saw with the delta function. So like we did earlier, we'll basically separate our potential regions into threes. Region 1 and 3, we have a potential that's at 0. Then at region 2 is where we see the finite well. And like before, we'll write down our time-independent Schrödinger's equation to identify forms of solutions. So as we can see, as we isolate the second derivative of psi, the form of the equation becomes identical to the form of the equation for the delta function. Now, of course, we have to remember that the potential is a function of x. So when we say E minus V, that's going to have different amounts depending on whether or not we're in regions 1, 2, or 3, which is going to affect our k value. However, the form of our equation is going to be the same. And we saw in this case, with a second derivative equal to a negative k squared of the original function, that we're going to have sinusoidal based behavior, or e to the plus or minus I kx. So how do we interpret that? Well, we'll basically use the same approach as what we did before, where we have some a e to the I kx. We could think of this as our incident wave, and then we're going to have some sort of reflection, b e to the negative I kx. But then within region 2, we'll have some additional behavior. We'll have some of the wave continue through with a c e to the I kx, and some of it come back. Now, these are just mathematical solutions to this form of the equation. Finally, if we look at it just mathematically, we'll have in region 3 f I to the I kx and g e to the negative I kx. And just like we did here, we know that this g is going to go to 0. You can't have some random wave coming in from infinity. So this leaves us with something very similar to what we saw with our infinite delta potential well. Just looking at the wave equation solutions for each region, we're left with these three equations, which we can use to identify transmission and reflection ratios the same as we did before, simply by bringing in our boundary conditions and using these three equations here. Those boundary conditions being psi of 1 at negative a equals psi of 2 of negative a. In addition, psi prime at negative a equals psi 2 prime at negative a. And you could do the same for positive a. In summary, we've taken a first look at a free particle interacting with a finite square well. We've seen that the overall behavior is very similar to a free particle on a delta function well. And by looking at the forms of the equations for the solutions, we know that we will be able to set up some sort of ratio for transmittance and reflectance. The next step is to identify those solutions and take a look at the behavior and identify interesting characteristics. I look forward to exploring that with you next time.